All right, lecture 21. This is the last lecture on chapter 8, which is still aimed at increasing efficiency of vapor power cycles. We're going to go through a cycle with regeneration with a closed feed water heater. We had the open feed water heater in the previous cycles. And then we'll describe a few more complex vapor power system configurations and vapor power systems with other working fluids to a certain extent. So closed feed water heaters. Basically, they are full heat exchangers. The open feed water heater was a mixing chamber. Here we have a heat exchanger, and we're going to increase the temperature of the feed water by using enthalpy from the extracted steam that condenses in a tube heat exchanger. Now, in this case, the two streams do not mix. In the open feed water heater, you had the bleed steam from the turbine that was mixed with the condensed water that you're going to send back into the boiler. Here, these two do not mix in the mixing chamber, which means that they can be at different pressures. That's an advantage. The disadvantage, of course, is that it's more complicated. There are two different approaches. In the first approach, you have the bleed steam that comes from the stages in the turbine. Extraction steam is sent through a heat exchanger. So it is exposed to the feed water, that is the water that comes from the condenser, and is pressurized. Here, this steam condenses, and the condensate, which is liquid water, is then pumped to a higher pressure line where it meets the feed water, which is at a higher pressure. The other approach is where you take the steam that's extracted, that's bleeded out of the turbine, you go, just like before, through a heat exchanger where it's exposed to the feed water and condenses. But now the condensate, you're going to adjust through essentially a throttle that will lower the pressure, and you will now inject it at a lower pressure point. So this extraction steam essentially can be either sent at a lower pressure or at a higher pressure. This takes a pump. This just takes a throttle. All right, so let's go over the details of how such a regeneration cycle will work. So in this particular case, we're going to look at the case where the main steam line goes through the high pressure turbine, and then there is bleed steam that comes out of here, sent to the condenser, so where it's exposed to water that comes from the pump, and condenses. Now, in the particular case that I will describe here, this condensate is then sent through the trap to low pressure. So, fraction Y of the flow is bled and exposed in the closed feed water heater to the lower temperature water that's inside the tube, the feed water. It condenses, so at stage 7, it's liquid water that's condensed, which is then sent through a trap between 7 and 8. In the trap, it loses its pressure, but it keeps its enthalpy. And then at 8, it is mixed with a fraction 1 of 1 minus y that came from the second stage of the turbine. It's back mixed in this particular case in the main condenser. So that the water flow that comes out of the condenser at point number 4 is the full water flow that you had point number 1. And the second stage of the turbine is the only place where you have 1 minus y. The mixture, which in open feed water heaters happened in the feed water, happens now in the condenser itself. So that is what I'm saying here. The total liquid flow at state 4 is the same as the main flow of liquid through the main line, through 5, through 6, and through 1. Okay, so let's describe a little bit how this looks on a TS diagram. At point number 1, like before, we start with superheated steam. The first turbine stage expands from 1 to 2, and at point number 2, we bleed a fraction y down toward this point number 7. We'll get that in a minute. So we bleed fraction y. The fraction 1 minus y continues from 2 to 3, in the condenser where it is condensed. Well, where is it condensed? Well, it condenses to 0.4 ultimately. But what happens in the feed water heater is that the enthalpy that comes from point number 2 is used to condense the water that was in the steam, to condense the steam that was in this line, in the contact with the cold water that comes from the pump. That steam is condensed at point number 7, which is on the saturated liquid line. Then it's sent through a trap. The trap is a thing that keeps the enthalpy constant but reduces the pressure. So an isenthalpic line on the TS diagram looks like this dashed line here. The work of the trap is going from 7 to 8. And then once we are in 8, we mix with the steam that comes to 3 so that the final condensate at point number 4 here is saturated liquid, which then goes, like in a classic Rankine cycle, through the compressor, 5 to 4, to the pump, 5 to 4, and then it is heated up partially from 5 to 6, 5 to 6. The temperature is increased along this isobaric line. So the pressure P5 equals pressure P6, but it's different now from pressure P2. And the temperature goes up. 6 is then at the higher temperature here. And it's this liquid that's then fed into the steam generator, where it's heated all the way up to 1. So that's why this thing is so useful to increase the enthalpy, is because the heating from 5 to 6, which is at low temperature, happens before you have gone into the steam generator. Now we have to, of course, write the energy balance of the closed feed water heater, which is a conventional heat exchanger. So mass flow of Y times enthalpy 2 minus enthalpy 7 equals mass flow of between 5 and 6 times enthalpy 6 minus enthalpy 5. Now this is the main mass flow, so this is fraction 1 of the m dot 1 times H6 minus H5, which is here, must equal to the fraction y that came from 2 to 7. Fraction y times H2 minus H7. That's the energy balance in the closed feed water heater. This, again, is something that is solved for y, H6 minus H5, H2 minus H4. Now, the trap has its own energy balance. Because it's a throttle, it simply means H8 equals H7. There you go, or H7 equals H8. And so these are the equations you then solve for to find fraction y. The rest is a conservation of mass and of enthalpy, like we did for the classic Rankine cycle. And here is the functioning of the closed feed water heater. Let's now change gears and put this whole thing together. So, when you look at a real power plant, you have a turbine that comes in many stages. Here it's shown with 6 stages. There are stages between 1 and 2 where you go through a closed feed water heater. Between 2 and 3, you have another closed feed water heater. Between 3 and then 4 and 5, you have a reheat step. Then you go 5 to 6, you have another open feed water heater here, and I'll get to that in a minute. Here we go through a closed feed water heater, and here we finally go to the condenser. All right. We have one open feed water heater. The reason is that when you have this mixture of steams, you can take out whatever air or other gases get dissolved in your water. Water goes through these cycles many a time, and that water doesn't stay always clean. The thermodynamics of the cycle are all calculated assuming you have pure water, but you don't. Eventually there are small leaks, especially because this condenser is under atmospheric pressure, so any small leaks gets air into the system. And once you have air in the system, the thermodynamic properties of the water are degraded, so you have to get that air out. Now, the solubility of a gas in a liquid is decreased when you increase the temperature. If you're going to get air in the system, that air will dissolve in water at the lowest temperature here. If you want to get that air out, you have to heat up the water. And that is why you can use this open feed water heater at the same time to preheat 11 to 12 with this, and that is where the air will actually come out. So you can pump that air out here with a small pump. The other thing you notice is that you use closed feed water heaters as much as you can ahead of the open feed water heaters. So because these pressures, P2 equals P15, but it's different from P14 minus P21, that gives you flexibility as to what you're going to be doing with the water in 15. For example, you can send it back in a second closed feed water heater here, or you can mix it with 3, and then use that, adjust the pressure again, to put in the open feed water heater. Once you have an open feed water heater, there's nothing else you can do but send that water back into the main stream. The closed feed water heaters, you can feed into each other, or eventually you can feed them into an open feed water heater. So that is a classic cycle. Now at this point, you have noticed that you have 21 points. So you have 21 lines in your state equations. And this becomes quite an exercise in bookkeeping, in solving problems with real vapor compression systems. Okay, let me give you a few data to close this off. First of all, most of the energy that we have produced in this country really comes from that. In fact, if you look at, this is again the fraction of energy in the country in 2002, if you look, 26% of the energy we use is really electrical energy. That comes from the electric power sector, whereas only 21% comes from transportation. So this is the biggest producer of energies. Secondly, you will notice that we have a fraction, 11.9 quadrillion BTUs, that's actually produced as electricity, and you have a fraction of heat losses that is 26.3. Sorry, the total electric power sector burns 38.2 quadrillion BTU. That's either as loss or as electric power. Now, the ratio, therefore, of electric power over the total, that is work over work plus Q out, which is Q in, is the efficiency of the system. And the efficiency of the system, therefore, is 12 over 12 plus 26 is 31%. So that's an average over all power plants in the country, some of which are 80 years old and some of which were built last year. It's a large number. It's much better, for example, than the efficiency of the transportation sector, which is 5 out of 25. But still, it's not near 50%. Here is another piece of data. We have here plotted the carbon emissions, that is in kilograms of CO2 per kilowatt hour. And typically carbon emissions are higher with coal-fired plants, and also they're higher when the efficiencies are lower. So these are the low efficiency old plants. And here's the total amount of power generated by them, megawatt hour. So you'll see that most of our power plants are actually moderately, they emit a lot of CO2. First of all, because they're coal-fired, and second, because they're not that efficient. We have a lot of plants that are quite inefficient. Typically, these things are 80 or 100 years old, or so, well, 100 I don't know, but 80 years old plus. The more modern plants now burn gas, natural gas, and they come, as you can see here, in 2 generations. Some that emit 0.6, some that emit 0.4 kilogram of CO2 per kilowatt hour produced. And these are, of course, the more modern plants. Now, so the average is 31% efficient. What do we have with modern plants? One of the producers of power plants is a Belgian company, Suez Electrabel. They will sell you power plants. And here's their product lineup as of today. The most beautiful, efficient power plants have topping cycles. We haven't gotten into topping cycles yet. I'll explain in a minute what they are. But typically, you have a high temperature cycle that is, for example, a gas turbine, which we'll see in chapter 9, and a low temperature cycle, which is the water vapor system that we described in chapter 8. The reason you do that I will explain in a minute. But if you put these two thermodynamic cycles together, one as a topping cycle, the gas turbine is a topping cycle, and the vapor cycle as the bottoming cycle, you can get to efficiencies of 58.1%, which is fantastic. These plants produce, say, 400 megawatt power, and the price is on the order of 220 million euros, which is 250 or so million dollars. Modern coal-fired plants use pulverized coal, typically very, very large plants, 770 megawatt. Their efficiency is somewhat lower, and they actually cost more. Now, very often nowadays, there are either plants with topping cycles or cogeneration plants where you use the heat produced for other useful functions. And typical suppliers of parts for power plants are General Electric, Siemens, Alstom, and companies that I don't remember what they are. All right. So what is a topping cycle? Well, in essence, in your power plants, if it's gas-fired, you have temperatures of gases which give these blue flames, which are 2,000 degrees centigrade or some such thing. If they're coal-fired, the flames are yellow. The reason is that there still are little particles of carbon in there that gets heated up, not quite as high as the gases are here because they're solids, and then they re-emit light because of the heat that they reach. But these flames are at a lower temperature because these gas particles are, these coal particles, dust particles, are at lower temperatures. Nevertheless, they are far, far in excess of the temperatures of even the superheated steam that you sent in here. So here is this steam generator, basically. You will have coal that's pulverized, and that's blown as dust to make the flames. It looks like this. The ash comes out of the flames. And of course, the hottest part of the boiler is the superheat stage. So that's this famous point number 1, which can be supercritical, so 520, 550. The non-critical ones are 480 or so degrees centigrade. But still, that is a very, very large distance in Kelvin away from the temperature of the flames. So after the superheat stage, the next lower temperature is the reheat stage. The next lower temperature then is the preheat stage in which you send water. Now, the problem is that you want to recover, that you want to address, is the big difference between the flame temperature and the water temperature, even in the superheat state. And a thermodynamic cycle that works on this temperature difference, that is then going to be called the topping cycle, makes use of that temperature difference. Classic topping cycle, if you use gas, natural gas as a fuel, is to burn the natural gas in the combustion chamber of a gas turbine, we'll see in chapter 9, and then use power from the gas turbine as a topping cycle, use the exhaust of the gas turbine to heat, to superheat the water or the vapor in a conventional bottoming cycle, which then is, in fact, like this, a Rankine cycle or a vapor cycle, vapor generation cycle. So topping cycles make use of the temperature difference between these two. Now, cogeneration cycles are things that make use of the temperature of the water that leaves the low pressure turbine. You don't need to send that water directly into a heat exchanger that you then send into the river. You could have here water temperatures at 40 or 80 degrees centigrade, which you can still use to do something with. Well, that something is then called the cogeneration. So let's look at one of these each. A very old and luckily abandoned now idea for a topping cycle would have a Mercury cycle. So in the TS diagram, we have water that has a vapor dome that looks like this, where the critical point up here is on the order of 520 degrees centigrade. There are other things that have these vapor domes that reach much higher temperatures, like mercury. Unfortunately, mercury is toxic, and so you really don't want to do this. But it's an example of what could be done. So you can then construct yourself a Rankine cycle with vaporized mercury, goes through a turbine, gets condensed, goes through a pump, back to a mercury, of all things, vaporization cycle. And then the temperature, the heat that's extracted from the mercury when it condenses is in turn used to operate a second cycle, which would be a water cycle. Pump, the water would be preheated with heat from the mercury, then sent in the top end of the steam superheater, and then sent to a water steam turbine, condenser, and pump. So that makes use of the low position of the vapor dome in water and the high position of the vapor dome of mercury. There are much better ways of doing this. A cogeneration cycle, on the other hand, is one where you take part of the heat of the turbine. So here you have a conventional steam generator that sends you into a turbine. You can use bleed water from the turbine, or you can use the full exhaust of the turbine into a condenser, or you can use bleed air in a system that would require heat at a certain intermediate temperature. You could try to use this heat, or you can try to use heat here for other useful purposes other than generating power from the turbine. That's then called a cogeneration plant, and it's another way to get some use out of heat that you would otherwise completely lose into the rivers. And that's it. Thank you.